Hello, my name is Catherine Rayax. I am a postdoc at Michigan State University, and today I'll be talking about not Floer homology and relative adjunction inequalities. Before I get started, I'd really like to thank the organizers for putting together this conference. And I also want to say that if you have questions, please don't hesitate to leave me a comment. I'll be checking those throughout the 2 weeks. And especially for graduate students, if you have questions, please come see me in office hours. I'm going to have an hour on June 3rd, starting at 4 p.m. The first thing I want to talk about today is just a general set of problems that I'm going to refer to as four-dimensional genus problems. So before I say that, let me just say for the duration of the talk, all of the manifolds that I discuss are oriented and smooth, working only in the smooth category. Okay, so the first four-dimensional genus problem I want to discuss is the one that I've sort of indicated over here with this picture. Let's say I have some closed oriented four manifold, and if I fix a two-dimensional homology class A in W, in H2 of W, I can ask what's the minimal genus surface embedded in W that represents that class. So here's sort of one possible surface. And in general, this can be kind of a hard problem. And so we often look for lower bounds. And one sort of important lower bound comes to us from both Seiberg-Witten theory and also Hegardt-Floer theory. It's known as the adjunction inequality. So it gives a lower bound on this quantity. What I'd really like to talk to you about today is a relative version of this problem where I start with a four manifold. Now it's a four manifold with two boundary components, y1 and y2. And I want to also fix two knots, k1 and k2, in either boundary component. And then I can ask the question, what's the minimal genus of a surface that interpolates between these two knots? So here's a surface, and I should also say, I should also fix a homology class for sigma in H2 of W rel boundary for this to make sense. So this might be somewhat unfamiliar, but there's a special case that's hopefully more familiar to people, which is just the question, what is the four-ball genus of a knot? And in that, to ask that question is to sort of start with a four-ball. It has boundary S3, and I'm fixing a knot in the boundary, and I'm just asking what's the minimal, the four-ball genus is the minimal genus of a surface that has boundary that's not. And there's a particular lower bound, again, that comes to us from Hegardt-Floer theory, which is this invariant called the Ojvath-Szabo tau invariant. So Ojvath and Szabo proved that tau of k is less than or equal to the four-ball genus of k. Okay, and so today, what I really want to do is discuss how do I sort of generalize this to the setting that I've outlined up here. So what is this Ojvath-Szabo invariant was originally defined only for knots in the three-sphere. So I want to define this invariant more generally for knots in any three manifold, and then I also want to develop to discuss some analog of this bound. Okay. So in order to do that, let me just tell you a little bit about the structure of Hegardt-Floer homology. So let's start with a knot in a three manifold, and I'll say let's assume our knot is at least rationally null homologous. So it represents a torsion class in homology of Y. Then this information of the knot in the three manifold can be specified by something called the doubly pointed Hegardt diagram. So here's a surface, some curves on the surface, and two base points on the surface. And basically what this is this surface and set of curves specifies a Hegardt diagram, a Hegardt splitting for a three manifold, and these two base points are specifying an embedding of the knot in the three manifold. Okay, so if we forget about the Z base point, there's a way of extracting from this information a chain complex, the Hegardt-Floer chain complex associated to this Haggard diagram. And then if we go ahead and take homology of that chain complex, we get an invariant of the Haggard-Floer homology of this 3-manifold, or HF hat of Y. So this is just an invariant of the 3-manifold. On the other hand, if we remember that Z base point, we remember the knots embedding in this 3-manifold, and there's a way of assigning a grading to the generators of our chain complex. This is called the Alexander grading, and it depends on the knot, and in particular on these 2 base points. So it's really, I mean, it's just a map from the generators of our chain complex into the integers if our knot is null homologous, or the rational numbers if our knot is rationally null homologous. And I'll just remark that if you take the homology of the associated graded with respect to this grading, that's what's known as HFK hat, or the knot Floer homology of K. Okay, so that's kind of a basic overview of how Floer homology and knot Floer homology are related. And now I can define this invariant, the tau invariant. So I just want to take a class in HF hat of my 3-manifold, and I get an invariant associated to this class by looking at the minimum Alexander grading over all generators in CF hat who represent the class alpha in homology. So that's just some number, and we call that number tau alpha. Okay, so now I can bring us back to the problem that we talked about before. Here's our 4-manifold with boundary components y1 and y2, and our knots k1 and k2. Floer homology, or Floer theory, also tells us that this 4-manifold is going to induce a map between HF hat of this boundary component and HF hat of that boundary component. And it's really important to know that this map is highly dependent on the 4-manifold that you're looking at. So maybe there's different 4-manifolds that have the same boundary. They might induce different maps on Floer homology. But anyways, so the theorem says the following. This is our relative adjunction inequality. If this map induced by my 4-manifold sends the class alpha to the class beta, then I have this inequality, which is a lower bound for the genus of this surface sigma sitting inside of my 4-manifold. Notice here I have the difference of these 2 tau invariants, the one corresponding to alpha in y1, and the one corresponding to beta for k2. And then there's these extra terms that really are somehow they're really dependent on this homology class that we fixed for sigma. Okay. So let's look. I think it's helpful to look at an example. So sort of first nice examples are knots in S1 cross S2. So actually, before I talk about that, let me say something about the 3-sphere. So HF hat of the 3-sphere is just F2 as a single generator, and so that tells me that for any knot in the 3-sphere, I get a single tau invariant. There's only one class here, and so there's only going to be one invariant associated to that class, and that really is Oshwap and Szabo's tau invariant. Okay, so now let's think more generally about this case where we have maybe a knot in S1 cross S2. So first of all, what's the Floer homology? Well, you can calculate it. It turns out to be 2 copies of F2, and they have different homological gradings. So I've denoted the homological gradings here. And you can see this one's bigger than that one. So we'll fix a generator for this copy and call it theta top, and we'll fix a generator for this copy and call it theta bottom. So now any knot in S1 cross S2 has these 2 tau invariants, one corresponding to theta top and one corresponding to theta bottom. So now if we think about a knot in S1 cross S2, we actually get two potentially different tau invariants, one corresponding to this theta top, I'll call it tau top, and one corresponding to theta bottom, which I'll call tau bottom. And what I'd like to show you is that in different situations, you'll get genus bounds corresponding to maybe one of these or the other one. So let's first think about the 3-manifold S1 cross S2. It sort of naturally bounds to 2 different 4-manifolds. So we can see that it's the boundary of S1 cross B3, and it can also realize it as the boundary of D2 cross S2. So let's focus first on this example, on this 4-manifold. So here's my picture. If I remove a ball from S1 cross B3, then I get this cobordism from S3 to S1 cross S2. And let's go ahead and fix our knot on one end to be the unknot. Then asking about the genus of this surface is essentially equivalent to asking the question, what is the minimal genus surface embedded in S1 cross B3 that has boundary K? And we can go between the two by saying, okay, take this surface, cap off the unknot with a disk, and then we get the surface that has a single boundary component K. Okay, so we're looking at this 4-manifold, and if you compute the map on Floer homology that's induced by this 4-manifold, you see that it sends the generator of HF hat of the 3-sphere to theta top. Okay, so let's look at our relative adjunction inequality. Here it is, just write it down. It turns out that these are both going to be 0, as is the tau invariant of the unknot in S3. And so we reduce to just having that tau top is a lower bound for the genus of sigma. And so I'll write that as tau top of this knot in S1 cross S2 is a lower bound for the S1 cross B3 genus of K. All right. On the other hand, if we look at this 4-manifold instead, D2 cross S2, and we go ahead and remove a 4-ball like we did before, then we can play the same game. It turns out, however, that this 4-manifold induces a different map on Floer homology, and in this case, the map sends a generator of S3 to theta bottom. Okay, so now we get that tau bottom of K is a lower bound for the D2 cross S2 genus of K. And let's see how this plays out for a specific knot. Okay, so here I've drawn a picture of a knot in S1 cross S2. This is a 0-frame 2-handle. So the 3-manifold indicated here is S1 cross S2, and this is my knot sitting in there. If you calculate, it's not so hard to calculate the tau invariant for this particular knot. And if you calculate tau top, you get 1. On the other hand, if you calculate tau bottom, you get 0. So what does that tell me? Well, first of all, it tells me that the S1 cross B3 genus of this knot is bounded away from 0, and therefore K does not bound a disk in S1 cross B3. On the other hand, we're not really getting any information about the D2 cross S2 genus. However, you can actually show by hand in this case that this knot does bound a disk in D2 cross S2. So for the rest of the talk, what I want to do is go through a few applications of our theorem to different kinds of topics. Okay, so the first one is that out of our construction, we also obtain genus bounds for links. So let's fix a link in the 3-sphere, and we're also going to insist that our link be oriented. I can define the 4-ball genus of a link to be the minimum of the number of components of the link minus the Euler characteristic of sigma over 2, where sigma is some surface in the 4-ball that has boundary our oriented link. Okay, and what I'd like to do is use our tau invariants that we defined to construct genus bounds for links. So the tau invariants that we defined before are only defined for knots. And so the way we're going to get invariance for links is by using a procedure called notification. So let me say what that means. So let's start with a link in the 3-sphere. Here's an example. It's a hop link. I could try to turn that link into a knot by simply banding these components together. However, if I just do that banding procedure in the 3-sphere, it's not well defined. I could choose different bands and maybe get different knot types. So to sort of fix that problem, what I want to do is every time I add one of these bands, I want to make it go through a little 0.2 handle. And if I claim that if I do the banding in that way, what I get is in fact well defined. And what do I get? It's a knot called kappa of L, the notified link. And it's because I've added these handles, it's really a knot in some number of copies of S1 cross S2. And this is just the number of components of the link minus 1, which is just the number of bands that I need to add to connect all the components. So here's how you do this procedure for the hop link, and you'll notice that this notification, the notified hop link, is this knot in S1 cross S2 that we discussed on the previous slide. Okay, so tau invariance for links, how do we define them? Well, we'll just say that tau theta of L is tau theta of the notified link in some number of copies of S1 cross S2, and we get a tau invariant for every element of HF hat of this number of copies of S1 cross S2. So in particular for our hop link, we get that tau top is equal to 1. And from really this theorem is a sort of corollary of the relative adjunction inequality. We get that tau theta of our link is less than or equal to the 4-ball genus of this link. And so in particular, since tau top here was equal to 1, we get that this hop link does not bound a disk. So for a second application of our relative adjunction inequality, we get bounds on the rational genus of a knot. So let me explain a little bit of background on this problem. So first of all, let's think about just a knot in a 3-manifold. It's a fact that the knot bounds a surface in the 3-manifold if and only if the homology class of the knot is 0 in H1 of Y. And such a surface is called a Cipher surface for the knot. On the other hand, if the knot represents a torsion class, it won't bound a surface, but some number of copies of the knot bounds a surface. So you can think of this surface, in other words, as a surface that wraps some number of times around your knot. And given a knot, you can ask, what is the minimal genus of such a surface? And that quantity is denoted like this. It's called the rational genus of the knot. And it's a theorem of Ni and Wu that knot Floer homology detects the rational genus. And so what I mean by that is if I have a rational homology sphere and a knot in that rational homology sphere, the maximum Alexander grading achieved by an element of HFK hat is equal to the rational genus plus a half. And this is a really nice theorem. It has this corollary, which is that if I have a Floer simple knot, then that knot actually minimizes genus over all knots in its homology class. So if I took some other knot that represented the same class in homology, its rational genus is bigger than the knot that I started with, than my Floer simple knot, bigger than or equal to. Okay, and what is, so this is all really about the 3-dimensional rational genus, i.e. what kinds of rational ciphered surfaces exist for our knot in this 3-manifold. And what our relative adjunction inequality allows us to do is sort of push this into 4 dimensions. So we have this theorem that says if Y is a rational homology 3-sphere, then for all alpha in HF hat of Y, the associated tau invariant tau alpha is a lower bound for what I want to call the rational slice genus of the knot plus a half. And what's this rational slice genus? Well, here's sort of a schematic picture of what I mean. So if we think about, here's our knot in the boundary of y cross I, and remember our rational Seifert surface for this knot is some surface in y that wraps some number of times around the knot. But I could also sort of allow surfaces, sort of push these rational Seifert surfaces into this Floer manifold and ask whether, like, what is the minimal genus of one of these pushed in surfaces. So we'll call these rational slice surfaces, and we'll call the rational slice genus the minimum genus of one of these pushed in surfaces. And a priori, it seems like, well, if you allow the surface to be pushed in, the minimal genus could be smaller. And the corollary says, well, for Floer simple knots, that doesn't happen. So in particular, for a Floer simple knot, the rational slice genus of a Floer simple knot is minimal over all knots in the same homology class. And this goes along the sort of general mantra, I guess, that Floer simple knots behave like unknots. So what I mean by that is, if I think about how this works for knots in the 3-sphere, there's only one torsion homology class, it's the 0 class, and there's a single Floer simple knot in that class, namely the unknot. And the unknot bounds a disk in S3, and it also bounds a disk in the 4-ball. So in particular, if you take that disk in S3 and push it in, you can't lower the genus by doing that. Sort of has to stay the same. And this is saying that's not just a fact about the unknot, it's really a fact about these Floer simple knots. And what's sort of interesting is that these might not have genus 0. They might have some slightly larger genus. So the final application I want to talk about today is what I call a 4-dimensional Banneken bound. And this is an application to contact geometry and topology. So the classic Eliashberg Banneken bound is the following. It says that if I have a contact-free manifold, then this contact structure is tight if and only if for any surface embedded in Y with Legendrian boundary, I have that the Thurston-Banneken number plus rotation number of the boundary is less than or equal to the negative Euler characteristic of the surface. And what I'd like to conjecture is that this is not just a sort of 3-dimensional phenomenon, but it's really a 4-dimensional phenomenon. So in particular, the contact structure is tight if and only if for any surface embedded in not just Y, but Y cross I with Legendrian boundary in one of the ends, then the Thurston-Banneken number plus rotation number of the boundary is a lower bound for minus the Euler characteristic of the surface. So again, it's this kind of statement about not being able to sort of do better by, in terms of genus or Euler characteristic, by allowing your surface to be pushed into Y cross I. So what evidence? Why am I making this conjecture? What evidence is there for this conjecture? Well, we have this theorem, which says that if we have a contact-free manifold where the contact invariant, the Heegaard-Floer contact invariant, is non-zero, then we actually do get this bound. So this is an application of the relative adjunction inequality. So one example is the case where Y is the 3-sphere. In that case, we know that a contact structure is tight if and only if it's the standard contact structure, and in that case, we also know that the contact invariant is non-trivial. So we actually do get this if and only if for the case where Y is S3. And this was already known. This is really just recovering what's known as the slice-Banneken inequality. So our conjecture is really that this kind of holds more generally. On the other hand, you really can't use this theorem to prove the conjecture because we know that there are 3 manifolds with tight contact structure, but whose contact invariant is equal to 0. So this won't be enough to prove the conjecture. All right, so thank you for watching my talk. Again, if you have questions, please leave me a comment or come visit me in office hours on Wednesday. Okay, bye.